All right, hello. My name is Elizabeth Brown with the International Board of Safety Professionals. Today we'll be discussing electrical safety. And regarding the reference that we'll be using is the OSHA standards that are found in Part 1910.302, which are the general industry standards that, for the most part, construction standards, maritime, all the other standards also utilize these, but these do specifically apply to the general industry standards. Okay, again, the OSHA standards cover numerous electrical hazards across various industries. When we mention general industry, that's a very broad term that covers any industry, honestly, that's not covered by the construction standards or those that are in shipyard or maritime standards. There are specific standards for those specific activities, but in general, the general industry standards that we'll discuss today do cover and address most commonly found electrical hazards in workplaces. The OSHA standards are derived from the National Fire Protection Association standards found in the NFPA 70 standards in terms of their electrical standards. We'll also talk about the NFPA 70E standards that address arc flash safety. And then we also will reference the National Electric Code that OSHA utilizes for their electrical safety standards. Again, the construction industry has their own specific set of standards for found in Part 1926, Subpart K. And then in terms of maritime, they also have their own sets of standards for marine terminals and outlined in Part 1917, longshoring outlined in 1918, and again, the general industry standards are found in 1910. Maritime also has standards for shipyard compliance found in 1915, but those will be topics for another session. All right, just some basic understanding about electricity. There are two kinds of electricity. Static electricity or stationary electricity is something that we've probably all experienced, especially where I live. I experience it in cold weather climates when there's less humidity. And that's when, maybe I'm walking on carpet and a little static electricity develops between like from friction from two different types of materials rubbing together. We also can experience static electricity can actually cause us a lot of problems if we have a static electricity spark pop up and we are pumping gasoline or distributing other types of flammable liquids through pipes. And that vapor off that flammable liquid is very ignitable in certain for certain really highly flammable liquids, and the static electricity spark can cause that vapor to ignite. So to me, when we think about static electricity, it's not the most dangerous thing or the thing we have to be concerned about because it is stationary, but it can cause a lot of challenges in the workplace. But for the most part, our electrical safety standards are mostly focused on dynamic or moving electricity. And that's the electricity that we have, like you see in the picture here, where we have a current flowing from a power source that is directed at powering our equipment, our lights, all the things that keep our facilities running. And we can have direct current electricity, and we also can have alternating or AC current electricity. So it's important that we understand how electricity behaves so we can understand the hazards associated with it and to control those hazards. So you can see this example of the dynamic electricity with the battery here going to a light, and you can see the essential shape or the flow of the electricity is a circle. right? We're creating a circuit. The electricity flows, or the flow of electron goes out of the negative terminal, goes to the light, and then flows back to the positive terminal. And then the current direction of the current flowing flows from the positive terminal to the light. And then that negative, there's a wire connected to that negative end. And when we make a good contact with those positive and negative, then that current should flow, and the light should turn on. Where we'll see several times in this presentation that a worker or ourselves can get injured or even can be killed is if, obviously, if we're touching a higher amount of current and voltage than just a small voltage battery here. But, some type of energy source, a fixed energy of electricity coming into a facility like 110, 120, 240 volts, 480 volts, 220 volts, on upwards. And we somehow touch the positive and negative, or the positive or the wire with current, and we have a good contact with the ground, then we become a part of that circle or a part of that circuit. And that is not good news for someone. It would definitely end up in a severe injury or death. A very fundamental law that we have when dealing with electricity is Ohm's law. So this is important in understanding just how electricity works. Ohm's law tells us that we have an electric current that flows through a conductor, flows between 2 points, and that is directly proportional to the voltage across those 2 points. So you see, we've got some diagrams here, but Ohm's law is essentially, we can look at it as voltage equals current times resistance, or to work that in a different way, if you're trying to figure out what is the resistance of needed, you would multiply, or you would divide voltage by current. And if you needed to know what is the current flowing through this circuit, you would divide voltage by the resistance. So you can see in the diagram on the left here, we have the source where we see those 4 lines in a row. That could be a battery, or that could be your voltage or your electricity source. And then we have a hot conductor, or the positive end of that, a wire flowing to the load, and that's the resistance. And then you also have a wire flowing, it says neutral conductor, and that would go to back to your source, and then could also potentially, depending on your circuit, go to a ground point. So many plugs on equipment that have a flexible wire will have a ground point, so acting as a point of protection for that voltage to go to the ground. So this is essentially how electricity works. We have these 3 essential ideas. Current, I like to think of it as, if we think of a river, the current is like the water flowing into the river. The voltage is kind of the amount of force pushing that water, and the resistance is maybe rocks or things that might say the river narrows in a spot and the water doesn't have as much room to go through. That is a way of thinking of resistance. So let's look at some electrical hazards to understand, so then we can focus on how to protect people from these hazards or protect our employees. So an obvious hazard with electricity would be an electric shock. Generally, those are experienced by individuals on their hands, because our hands are our tools, whether we're holding other tools, working with equipment, but these are our main tools. So those are the main areas where we generally experience electrical shock. But they're oftentimes, especially with higher voltage electricity, there will be an entry and an exit electrical burn, and you can see that on the hand. And then I've seen examples of electrical burns that have gone out people's backs, have gone through someone's foot. So that means that the electricity went through that person's hand, traveled through their body, generally across the really important organs of our body. And the other electric shock burn is the exit of that electrical current, because the electricity's goal is to get to the ground, and whatever gets in its way will, can be damaged by it if it's not, being properly contained. So if an employee ever experiences an electrical shock and you see burns in their hands, especially if it travels through and you have an exit burn on the back or anywhere else on the body, they need to seek immediate medical attention. This would be a medical emergency, because you can think about that electricity could have flowed through the heart, lungs, or any of the other organs and created a lot of damage. The other types of electrical hazards that exist are arc blast. We'll talk about that specifically in a few minutes. Other physical hazards that we experience are that could cause property damage are electrical fires and explosions. Those are the explosions in particular can be related to arc blast. And then lastly, we have this secondary type of hazard called the falls. So a lot of times electrical workers will be up on a ladder or some elevated area working on electrical wiring, maybe replacing a light or a ballast or replacing wiring. And if they get shocked, say we're on a ladder, when a person gets shocked, it's a very reactive state they're in, and the first thing their body is going to want to do is get away from that hazard, get away from that electricity. And so that's why falls are considered a secondary hazard, because a lot of times when I'm getting away from that electricity and say I'm on a ladder, I'm not really thinking about being on the ladder. I'm just trying to get away from that dangerous electricity, and I may fall off the ladder. So the first hazard we talked about was electrical shock. That occurs when both wires of an electrical circuit, if a person is touching those, as we see in this picture here, so both the positive and negative wire, we generally see those wires in colors of black is positive, or black is neutral or negative, and red as the positive or hot wire. But I have definitely seen situations where that was not the case. So we always want to, if we're a qualified electrical worker, we want to test all wires to ensure that we understand what we're dealing with and not just assume that black is neutral or the ground and red is the hot wire. Another way that we can receive electrical shock is if one of the energized wires, and we come in contact with one of those wires and the ground. And then we also, if a part of a machine is not grounded properly, and say an employee touches the housing of the machine, especially if it's metal housing, which metal is a conductor of electricity, and they're in good contact with the ground, that's another potential area where a person could receive an electrical shock. Now, the severity of the shock that a person receives depends on several factors. So first, how much current is flowing through the body? What is the path that electric current takes? So we talked about, an entry electrical shock burn going through the hand, and then an exit burn in their back or their foot, and that path went all the way through their body. And it's in a large amount of current that could cause severe damage or death. And then also the duration of time that the body is part of the electrical current. So in the United States, our typical housing wiring is 110 volts, 120 volts. And then we get into 240 volts, 480 volts are typical for maybe 240 volts is typical for, say, maybe something like our refrigerator or our washing machine or dryer, some of the larger appliances in our workplaces. 240 volts or 480 volts, maybe even 1080 might be needed for to run our big machines and equipment. So a lot of times people associate lower voltage with less hazard, but the lower voltage, like 110 or 120 volts, has a tendency to grip a person into the circuit for a longer amount of time. And so that means there's a longer amount of time for that electric current to flow. And so even though it's a lower voltage, that could cause a higher amount of damage to the person. So resistance plays into that too. So you can see here the amount of resistance on this table, and with the same amount of voltage can cause different experiences based on the shock intensity. In terms of when we have a larger amount of resistance, there's going to be less current that the individual is going to experience. And so there's just a sensation threshold. But then we see we have 12,000 ohms of resistance. There's more current that flows through the person's body, and it's painful. And then you see the least amount of resistance there can lead to enough current flow through a person's body that leads to death. You can also see over here on the table on the right that the effects of current and the bodily reaction. So you can see that all of these measurements in current are in milliamperes, or milliamps for short. So a milliamp is a 1,000th of an amp. And so it does not take much current flowing through a person's body for a person to experience extreme pain, respiratory arrest, and possible death. If you look in this range of 50 to 150 milliamps, and just to give you an idea of what that means, a typical like handheld power drill has about 75 milliamps of current flowing through it. So that kind of gives you an idea of a typical item we might use in a workplace that can cause extreme hazards and injury and potential death to employees. So we need to be very sure that we're taking care of our equipment, it's in good shape, and employees are not handling equipment that are damaged or in a way that they should not. Okay, we mentioned arc blasts earlier being a hazard. Arc blasts occur when we are in high amp currents. You see the top picture to the right. They're typically occurring in areas where we have motor control centers with really high amounts of amps and current. So maybe these big centers that then feed our equipment that have the lower amounts of current and amps. These can occur when we're switching. These can occur anytime that the current jumps from one conductor through another through the air. It generally happens when we're opening or closing the circuits, like I meant with switching, and that static electricity gets discharged, which typically seems to be a minor event that we experience when we're walking across carpet in our socks. This can cause a huge problem. As you see here, there's this huge fireball being blasted out at this person that's working in that room. So fire can occur, and also explosions are very common, and that's where that blast comes from. When this pressure of the fire is under pressure from this enclosed space, that fire has to blast out, and that explosion can occur. So just horrible things can happen from arc blasts. So molten metal can be blasted out at individuals, along with very loud noises. The person can also inhale the really high heat temperature, so it can burn the lungs. So for that reason, we have really strict policies to follow for based on the National Fire Protection Agency's 70E standards on arc flash and arc blast. So individuals that are qualified electrical workers that are tasked with doing these jobs have very specific and high levels of personal protective equipment they must wear based on the amount of current and voltage they're working with. We've talked about fire and explosion occurring and potential occurring for arc flash and arc blast. Electrical fires can also occur from ignition due to overheated conductors or equipment, which that can occur from overloading circuits. And then we also can experience that from just normal arcing or sparking as switch contacts. So these can lead to very drastic levels of property damage, and it obviously could cause potential personal injury to our employees. We talked about falls being a secondary injury to experiencing electrical shock, and this is a great picture to illustrate that a worker may be on a ladder working in an elevated location, and then they experience the shock, and so they fall back off of that ladder, and that fall itself can result in serious injury or death. So OSHA's standards in Subpart S on electrical safety gives us a lot of precautions and protective measures to protect employees from electrical accidents. So we'll go through those protective methods here, but essentially, if you can remember that anything over 50 volts must be protected by some method, whether it be guarding, insulation, some electrical protective devices, grounding, the use of personal protective equipment, and then also safe work practices. So there's a lot of different electrical protective devices that exist. Circuit breakers are very common. Those work to interrupt the electrical flow when they detect a fault, or if a circuit gets overloaded or short circuits, that circuit breaker will trip, and that will cut off the power source to just that circuit without having to cut off the power source to the entire facility. This helps to prevent damage and fires. So if you have a circuit breaker, and a fuse works very similar in a similar way. It's a meltable conductor that breaks the circuit in an overcurrent situation instead of just tripping it. So fuses, if they are utilized because they melt and they have to be replaced, where a circuit breaker just has to be flipped back open. But if a fuse melts or is broken, or a circuit breaker trips, as we call it, often that is a sign that something is going on with that circuit that we would want a qualified electrical worker or an electrician to address, so that we don't end up having some type of fire or some type of issue. Typically, it means that the circuit itself is overloaded, or there's something, some kind of issue with the ground, or something's causing it to short circuit. We also have overcurrent protection. So we have ground fault circuit interrupters. It detects a ground fault and shuts off the power to avert electrical shocks to employees. I think these are able to do this within 1/40th of a second of detecting a ground fault. So that's a fault for that circuit to going to the ground. OSHA requires that we have electrical outlets on ground fault circuit interrupters with anywhere we have with outlets within 3 feet of a water source. There's also residual current devices that cut off power when they sense current imbalances. That also reduces electrical shock risk. Surge protectors are we kind of call them power strips. It's just surge protectors that something you can plug your devices into, that if there is a voltage surge, it diverts the excess voltage away from the devices, and it protects the equipment from getting fried, as they say, from voltage spikes. There's also arc fault circuit interrupters that can be utilized in those big motor control centers that we talked about, that will identify electrical arc potential and prevent fires by cutting off the power. There's also isolation transformers that isolate input and output sides that minimize electric shock risk. There are protective relays. Those monitor parameters of electrical current and voltage, and it would trigger an alarm or a trip that going to equipment if it detects any abnormality. And relays have to be, coded or set by an authorized person to set those parameters so that might be specific to your equipment. And then lastly, we have safe work practice or safe grounding or earthing of our electrical current, so that we have a safe pathway to ground that reduces shock and fire risk. And here's some visuals, representations of what each of these devices look like. We have fuses. Again, those melt if there's an overcurrent. Circuit breakers trip. So we've got that blue little tab there. If it trips, it would be maybe in the down position, and then if you'd have to push it back up to reset it. Sometimes they toggle left to right. And then ground fault circuit interrupters are the picture on the right. Those can be put on at the individual outlets, and they also have ground fault circuit interrupters that are in line with the electrical extension cord. And then they also have ground fault circuit interrupters that can be applied to a circuit breaker, where it is on every item in that circuit. So, we commonly see these on the outlets, and you can see that they have a test and a reset button. So if it gets tripped, you can have to hold the reset in, but you also can test it to ensure that it's working properly. Another common electricity source that we need to be aware of is working around overhead power lines. And unqualified workers that are not in personal protective equipment should use the rule of thumb that they need to maintain at least, at a minimum, a 10-foot safety distance away from overhead power lines. And that includes themselves, any tools they may be holding, any equipment they may be in, like say a scissor lift. Nothing should come within 10 feet of those overhead power lines. And then there's a table in the OSHA standards that tells us that if we're over 50,000 volts or 5 kV volts, then, or I'm sorry, 50 kV volts, then the clearance needs to increase by 4 inches or 10 centimeters for each additional 10,000 volts. So, and that area is, anything above it, and we're talking about from the ground up, staying at least 10 feet away. This is very serious and something we should be very aware of. The electricity in these overhead power lines, those are transmission lines, and there's, as you can see, very high levels of voltage of that electricity. And we have to make sure that employees are not working near it, because that electricity can actually jump off of those lines. Those power lines are generally not insulated or protected in any other way. And so that's why we need to maintain that very large distance. Grounding ensures proper grounding of our electrical systems. That helps divert any excess current safely to the ground and reduces our chance of electrical shock and fire. Bonding, you can see, is another concept that can help protect us. So bonding is when we connect two electrically conductive things together. And then we have a grounding wire that will ground both of those things to the ground, instead of being short-circuited by this person holding that drill in the picture on the bottom. And just like we talked about earlier, the amount of current typically in a handheld power drill is 75 milliamps, which can cause severe electrical shock and potential death to that individual. All right, so guarding. So we always want to guard any live parts against accidental contact. Again, the rule of thumb is any live parts over 50 volts should be guarded against. A lot of control wiring now is 24 volts or less than 50 volts. It certainly would not hurt to guard that as well, but it's only 50 volts and higher that is required by OSHA to be guarded. And let's talk about what OSHA considers guarding in this situation. So guarding can mean by location in a room, vault, or similar enclosure that's accessible only to qualified individuals. Those rooms would need to be properly identified and labeled, also by suitable permanent substantial partitions or screens. Again, only have access for qualified persons to reach the live parts. And again, any openings into that should be guarded or located so that a person couldn't accidentally contact the live parts. And then also by location on a platform or arranged in an area like on a balcony or gallery that unqualified persons couldn't accidentally access it. All right, so by elevation, we talked about a minimum of 8 feet for 50 to 300 volts and 8.5 feet for any voltage over 300 to 600 volts. These can be live and unguarded in any other way, but just by distance or by elevation. So those are the clearance rules there. And I've had an OSHA inspector get a measuring tape out and measure at a facility that had some live electrical equipment up on the ceiling in a facility and make sure that it reached that clearance rule. Okay, so with OSHA and with any type of safety management, we want to consider personal protective equipment for employees, but we want to consider it as a last resort. So the main reason for that is because personal protective equipment is not preventing the hazard from happening. It's not preventing this, electrical current from an employee being exposed to electrical current. It's just trying to protect them from it. So we want to use engineering controls. We want to use work practice controls. And we want to use personal protective equipment only after we have exhausted the potential of using those other more effective controls. But when qualified electrical workers are working with live electrical equipment, there is a requirement that they have the appropriate personal protective equipment as outlined by the NFPA 70E standards. And the equipment is based on what level of hazard risk category or arc flash risk that there is to the individual. And that is calculated based on a lot of calculations. There should be an arc flash study completed in your facility and there should be labels on equipment that would tell any individual what type of personal protective equipment they need to wear. But anybody working with live electrical equipment should at minimum be wearing rated insulated gloves that are rated for the voltage they're working with, and insulated tools. The tools are especially important that they're insulated because tools are typically made of metal, and metal is a conductor of electricity. Additionally, eye and face protection such as safety glasses, goggles, and face shields should be used. Flame resistant clothing or arc-rated clothing may be required. Electrically insulated boots or footwear is another level of protection for qualified electrical workers or those individuals that will be working with live electricity. Also, head protection. We have hard hats that are designated as E or designated for specifically electrical work. And they do have impact protection, but they also will protect the head from up to 20,000 volts. And then for high noise environments, we always want to have hearing protection. But if an employee is working somewhere where there's a potential for an arc blast, we want them to have hearing protection as well, because those can be very loud. Okay, so here's a figure of a qualified worker. Maybe it's this picture comes from the NFPA 70E. It's kind of a diagram showing that he's working in a piece of equipment, of high voltage equipment, to repair some frayed insulation to a wire. So he would need to be in wearing safety glasses as he is. He's wearing electrically rated hard hat. He's in insulated electrically rated boots, and he's going to be wearing insulated gloves. Here's an example of some other levels of personal protective equipment where we've got the hard hat and a face shield. This individual is also wearing a balaclava on for face protection that would be arc rated or flame retardant. And then his clothing would also be arc rated. They also have, for the highest level of protection, they have kind of a fully enclosed suit that we would may need to require employees to wear if they're working in a really high voltage environment. This worker on the right here is not doing anything right. It doesn't look like. This is kind of a picture. I mean, he's wearing a hard hat. He's wearing some gloves, but and it looks like he's wearing some boots. But maybe that power line, that distribution line, is not active. But in general, we should not be standing on any kind of elevated surface like that. Generally speaking, I'll see workers for our power distribution companies in bucket trucks where they're inside an enclosed bucket working on lines like that. And those offer an extra layer of protection as well. Okay, so we talked about also using work practice controls and engineering controls to protect employees. So in general, we never want employees working with live electrical equipment unless they absolutely have to. And so our preferable method of controls against electrical hazards is to use lockout tagout. And this is a very long-standing and commonly cited standard that OSHA is finds very important and very necessary. And that is controlling hazardous energy sources. And that is found in 1910.147. And so we commonly call it lockout tagout, but the actual name of that standard is the control of hazardous energy, or like I said, lockout tagout. It is designed to prepare practices and procedures that disable equipment or the flow of electricity or any other hazardous energy to the equipment so that it prevents the unexpected release of that hazardous energy while an employee is performing maintenance, repairs, or servicing equipment. It's important to point out that while a big focus for lockout tagout is on electrical hazards, there's all types of hazardous energy sources that equipment can have, and we must control all of those energy sources before an employee may work on that equipment. The section also requires workers to follow safe work practices, such as the lockout tagout procedure that has been prepared, as well as making sure that employees that are exposed to any electrical hazards that are working near the equipment are aware of that and are not at danger. All right, so lockout tagout is a safety procedure used in workplaces. Every piece of equipment should have a written lockout tagout procedure that tells step by step an employee how to properly shut down and lock out the equipment so that all hazardous energy sources are controlled. Again, that can be electrical, mechanical, hydraulic, pneumatic, potential energy, gravity. All of those things are considered hazardous energy sources. And so we must safely dissipate any stored energy and de-energize the equipment. And then we're going to apply a lock or some type of device and a lock to make sure that that energy cannot be turned back on while the employees are working on the equipment. So like we mentioned before, the whole purpose of this is to eliminate the risk of any hazardous energy exposure during maintenance or repair activities. Physically locking out energy sources and tagging them with warnings has been proven to safely prevent any hazardous exposure or injury to employees that are working on equipment. This allows workers to know that they can safely work on the equipment without fear of being injured as well. All right, so OSHA has these specific requirements. Employers are legally obligated to comply with all the regulations of the standard and to protect workers when working on machinery, again, servicing, maintenance, or repair, or anytime we're removing a safety guard, or anytime we're having to disable some type of safety device like a light curtain or an interlock guard or anything like that, then we must follow lockout tagout procedures. Following the lockout tagout procedures has many benefits. There's really no negative to not following it, except not following lockout tagout is typically a shortcut and is the quicker way to get a job done, but is definitely not the safest way, and it's definitely not the legal way. So the benefits are, worker protection. So that's going to reduce injuries, reduce accident rates, and improve workplace safety culture. Workers that are not hurt are generally happier workers. So also, if we're have a safety culture that encourages looking out for each other and making sure we're following lockout tagout and putting these controls in place, will make sure that makes people happy, makes them feel valued, makes them feel like they can not be afraid of doing their job and doing it safely and correctly. It also enhances operator productivity. It minimizes the risk of injuries. Lockout tagout enables workers to perform their tasks more efficiently and effectively. It also reduces employer liability. So again, it not having employees injured from not following lockout tagout is going to reduce your potential of having a compliance audit. It'll protect you from legal liability. So following these rules and enforcing them is very important. So under the standard, we have some definitions. We have authorized employees. So that's any person who locks out a piece of machinery or equipment in order to perform servicing, maintenance, or repair on that machine. Affected employees are people whose job requires them to maybe they're the machine operator, or they are working around the equipment while it's being serviced or maintained. Maybe they're the cleanup crew, but they're working within that cell or around that area. Then they are considered an affected employee, meaning they are affected by that lockout tagout procedure. And we'll see in a minute that the affected employee must be notified when that work's being performed. And also when we're re-energizing the equipment, that those employees must also be notified that we're about to start the equipment back up and make sure that they're safe and not in harm's way. We also have energy isolating devices, which is a mechanical device that physically prevents the transmission or release of energy. And then we have our lockout tagout procedures or energy control procedures. These are procedures that should be developed and written for each piece of equipment, and any employee that is authorized to work on the equipment or affected by that lockout procedure must be trained on those procedures. Okay, so we talked a little bit about hazardous energy sources found in the workplace. It's very important that if you haven't already done so, that you understand all hazardous energy sources associated with all of the equipment in your workplace, and you've developed an equipment list and ensure that you have a lockout tagout procedure for each piece of equipment. And that it's very helpful to work in a team on this, because we want to ensure that we have considered all of these types of hazardous energy sources. So of course we have electrical hazards of generated and static electricity, mechanical hazards, thermal hazards, potentially, heat, chemical reactions, and we have types of potential energy that can be caused by pressure that's built up. We have hydraulic pressure, pneumatic pressure. Those things might need to be bled off or released. Vacuums, springs that might be compressed. And if we release something, it might spring out. And then we also have the potential of gravity. A lot of times when we release pressure in a hydraulic or pneumatic system, something drops because it might be, or it might shoot up because that pressure is keeping something in place. And so we need to make sure we use blocks, or we use something to prevent that gravity, that potential energy source of gravity, from causing any injury. We have types of lockout devices. OSHA says that we must use some type of lock, and all employees must use a lock. They say that it must be singularly identified. So meaning that we all use the same square red lock, or we all use some type of lock, because they want to make sure that the lock isn't confused for something else and an employee removes it and then turns a machine on while someone's working on it. So we want to make sure it's labeled. It says who is responsible for the lockout, and then it says, then we also have tags on there to make it really obvious that this is equipment has been locked out. It should not be removed, except for the employee that put it on. There should be one single key to that lock, and that key remains on the employee who put the lock on the equipment. But sometimes it's not easy to apply the lock to what you need to. So we have plug locks, valve locks, gate valve locks. There's also group lockout hasps, because every person who is working on the equipment must all have a lock on that equipment. There's different types of electrical locks, like there's circuit breaker locks. And then we also have different types of locks that can go on hydraulic and pneumatic and other pressurized systems. But the general procedure for lockout is that we prepare the equipment for lockout, and then we will shut it down. We will isolate all energy sources. We will lock and tag it out. Then we'll verify that all energy sources have been eliminated and controlled. And we'll do that by trying to turn the equipment back on. If nothing happens when we try to turn the equipment back on, then we can begin the work. And then once work's completed, we will reverse that lockout procedure and restore the equipment to service. So lockout procedures, so preparation, authorized personnel will identify all energy sources that need to be isolated and rendered safe. So that was a great time to look at your lockout procedure. And then we'll shut down the equipment following our standard procedures. And we'll turn off everything. So not just the off button, but we'll turn off any switches, valves, or other energy sources. And then we'll isolate the energy sources using locks, tags, or blocking mechanisms to ensure that the energy can't flow to the equipment or be accidentally energized or accidentally started. Then we'll apply our locks and tags to make sure to every energy source. To make sure that it physically cannot be turned back on. And then again, like I said, we will verify the energy source is locked out. By the workers must try to turn the equipment back on and ensure that it's de-energized and safe to work on. And then once that's the case, then maintenance, servicing, and repair may occur. And then once work is complete, we will remove the locks and tags, remove any energy isolating devices, replace any guards or safety devices. We'll notify affected employees that we're about to restart the equipment, and then we can return the equipment to operation following the proper procedures. There's some special situations to consider. If servicing on the equipment lasts longer than one shift, the next shift must come in, put their locks on the equipment, and then the other shift that's going home must remove their locks. And then that second shift must confirm themselves that all the energy sources have been isolated and controlled. Companies must create procedures for what are we going to do with contractors performing work at your workplace. If they have their own locks that are different than your locks, you need to make sure that all employees are trained and know about these different locks, and make sure that the contractors are following your procedures. And if a worker who applied a lock is not available, but we're ready to restart the equipment, you must have a procedure that's specific to your workplace on how are you going to confirm that the worker is in fact not still working on the equipment. So typically companies will develop a form that a supervisor must make an attempt to contact that employee at least 2 times. And if they do talk to the employee, sometimes employees have emergencies and they have to leave work and they forget to take the lock off. If the supervisor confirms the employee is not working on the equipment, then they can go and cut the lock off and remove it. Many lockout locks come with 2 keys, but I strongly recommend that the second key is destroyed and that only the worker has the key to that lock, just so that we are extra safe and no one else besides that worker can remove the lock, except for with using destructive means like a pair of cutting cutters to remove the lock. Once the and only a supervisor or manager doing that once they have confirmed that the worker is no longer present in the machinery. Okay, so in summary on our control of hazardous energy sources portion of this presentation, never attempt lockout tagout procedures unless you've been trained and authorized by your employer to do so. You want to make sure that you fully understand the procedures and all the equipment you need to use. Never lend or share your lock or key with anybody else. If every employee that puts a lock on a piece of equipment must take their key and remove that lock from the equipment. And that's just an extra set of confirmation, that an extra level of protection to ensure that no employee is still working on a piece of equipment when we're trying to re-energize it. We want to always be sure that our lockout tagout devices are compatible with the environment that we're going to be using them in. If it's a corrosive environment or a very humid environment, we want to consider that when we're purchasing those pieces of devices and locks. Okay, that concludes our presentation today on electrical safety and our secondary portion on control of hazardous energy sources, or lockout tagout, which is our main way of protecting employees against electrical safety hazards. Thank you for your time, and I hope you have a great day.